Hi everybody. So in today's video, we're going to be working on solving differential equations using a slope field. Now the idea here is that when we were using the process of separation of variables to solve a differential equation, we were using an algebraic way of finding the original function. What we're going to do today is create a visual representation, and this will allow us to figure out what the original function was by looking at the picture and the shape of the graph. So the first thing we're going to need to learn how to do is to create the graph of a slope field. In order to do this, you're going to do two different things. First, you're going to substitute, which means plug in, the x and y coordinates of the ordered pairs into the differential equation. Now, one thing we need to remember is that a differential equation tells us the slope of the tangent line of the original function. So once we have a value by plugging in our numbers, we can actually graph a little tiny piece of a line that has the slope that you calculated. And we're going to do this in the next problem. We probably won't do all of the points on the graph, but we'll do enough that you kind of get the idea of what this process looks like. So for part A, it says, on the axes provided, sketch a graph of the slope field at the points indicated. Now, I like to organize my work by kind of making a table of the x and y ordered pairs as well as the slope that I calculate. So I'm going to have x, y, and the slope that I calculate. Now I'm going to calculate that slope by plugging my x and my y into the differential equation that I was given in the instructions. So the equation that I'm using to calculate the slope here is this differential equation here. So I'm using that equation, I'm plugging in x and y ordered pairs. Now the ordered pairs are the coordinates of the points on this graph. So this point right here would have the coordinates -2, comma 2. And if I plug that into my differential equation, I would have -2 divided by 2, which is -1. So that's how I'm getting my slopes. I'm plugging them in. The next ordered pair right here would be -2, comma 1. And again, if I plug that in to my differential equation, I would get -2 divided by 1 because that's the x and that's the y, and that would give me -2. I'm going to keep going, and I'm going to kind of go through this quickly just to give you the idea. So I'm going to have -2, comma -1 is the next place on the graph that has a point, which means I would have +2 as my slope. I'm going to have -2, comma -2, which means I would have +1 as my slope. Next, I would have -1, 2, which is this point right here, which means I would have -1/2 as my slope. I would have -1, comma 1, which is -1 as my slope, -1, comma -1, which is +1, and -1, comma -2, which is +1/2. So I've got a bunch of slopes here, kind of give you the idea of how you're going to make this graph. Now here's how you would actually put this on the graph. So to graph these slopes, I have to think about what a slope of -1 means. What this tells me is that when the ordered pair is -2, comma 2, the tangent line to the graph had a slope of -1. Now, -1 means it's going downhill. More specifically, it's going down 1 over 1. So I'm going to look at a slope that looks kind of like this, a little tiny line that has a slope of -1. The next slope is -2, which is a little bit steeper. So I'm going to make it a little bit more like that. At -2, -1, I'm going to have a +2, so kind of the same steepness but the opposite direction. And at -2, -2, I'm going to have a +1. Now at -1, +2, I'm going to have a -1/2, which is a little bit less steep than this one. So if you imagine kind of going down 1 over 2, you'd be kind of connecting those two dots. So a little bit less steep. And then I'm going to have a -1, which means the same steepness for both of these, a +1, and a +1/2. So if you imagine going up 1 over 2, it would be like this. Now the rest of the points on this graph, I also need to kind of sketch a picture of. I'm probably not going to do them all, but let's do a few that I think would be helpful for the second part of the question. So let's add a few more little slope pictures to our graph. So the point 0, 1 would have a slope of 0. The point 0, 2 would have a slope of 0. The point 1, comma 1 would have a slope of 1. The point 1, comma 2 would have a slope of 1/2. The point 2 comma 1 would have a slope of 2, and 2 comma 2 would have a slope of 1. So I'm kind of just doing the ones that are up here to give you an idea of what this would look like. We need to think of what a slope of 0 would look like. A slope of 0 is going to be a horizontal line. So the little piece of the line that I'm drawing here will be horizontal, and the same here. This one's going to have a positive 1 and a positive 1/2. So if you imagine kind of going up 1 over 2, or you could imagine going down 1 left 2, it's a little bit flat like that. And then at 2 comma 1, I would have a positive 2, so a little bit steeper, and 2 comma 2, a positive 1. So that's kind of, if you imagine, you could probably see a pattern here. This guy's going to go like this, like this, like this, and like this. You're going to kind of see a pattern. All right, now the second part of our question asks us to do something a little bit different. So the second part of our question asks us to sketch the graph of the solution that goes through the ordered pair 0 comma 1. So first step is get it to go through that ordered pair. In other words, put a point on the graph on 0 comma 1. Now, one of the things we said in class when we did our investigation today was that a slope field is kind of like a wind tunnel. It shows you the general direction of the movement of the graph. So based on that, I can tell since the slope is 0 here, that's going to be a low point on my graph. Slopes of 0 are always going to be high points and low points, maximums and minimums. Following the graph, it looks like on this side of the graph, it kind of turns upwards, and on this side of the graph, it turns upwards. So if I was to sketch my picture, it might look something like this. This is not a science. You just kind of want to follow the wave. Don't overthink it. Follow the wave as best as possible. All right, now we can use this idea of sketching a picture of slopes and sketching a picture of the original graph to figure out what the original function would have been. So, one of the things we're asked to do on the AP test is to visualize the solution to a differential equation using a slope field. So, the directions will say estimate the solution used to a differential equation using the slope field. Here's how we do that. We can use a slope field to determine the solution to a differential equation by visualizing, I can spell, the original graph. So even though we're using a differential equation to sketch this picture, the picture we're looking at would have been the original function. Now, based on the shape of this picture, if I just kind of visually investigate this, it seems like the original graph would have looked something like that. Now, it could also have been located in other points. So, other places on the graph, it could have maybe looked like that, or maybe the original graph looked like this. But no matter where I start, the original graph has this kind of a shape like a U. That shape like a U gives me a clue about the original function. Since the graph is shaped like a parabola, it tells me the original function would have been quadratic. What that means is if I was trying to figure out what solution I'm looking for, it's going to be something that has an x squared in it, because that's what would give me the shape of a parabola. So it's going to be important here to kind of know the basic shapes of graphs that we've been reviewing all year, because that's how we're going to figure out what the original function must have been. Let's go ahead and look at the next page. So here's an example of how you can use the slope field to figure out features or what type of original function there would have been. So it says here, match each of the following slope fields with a possible particular solution to that differential equation. Looking at my slope fields, I've got some that look like waves and some that are kind of curving up, another one that looks like a wave and one that's curving down. And here I've got equations cosine, e to the x, e to the negative x, and negative cosine. Now, if I'm thinking to myself, gee, what does cosine look like? Back when I learned about trigonometry, I learned that cosine looks like this, which means close to the y-axis, the slope field should have these little horizontal slopes, right? There's a kind of a flat spot there. There should be another flat spot over here somewhere. And if I look for a slope field that kind of looks like that, that has a flat spot close to the horizontal axis and then goes down and then comes back up again, it looks like maybe that's going to be option C. If I kind of follow the wave here and just kind of ride the pattern, I'm going to have it go down and come up and then go down, which looks to me like a cosine graph. So I would say option C is probably cosine. Now, the other pattern that kind of has a wave would be option A, but the difference here is that this wave kind of goes up first. It starts low and then it goes up and then it comes down and then it goes up again. That looks like a cosine graph, but just kind of flipped over, which tells me it's probably going to be a negative cosine. So I would put an A here. Now, these two graphs look a little bit of a different shape. If I were to kind of follow the pattern here, it looks like this graph goes like this and then maybe flattens out in this direction. Now, I also happen to know that an e to the x graph looks like this, an exponential graph. So I would say that this is probably option B. The difference being that option C, where it kind of starts high and goes down low, would be more like an e to the negative x, so flip it over, which would be option D. Now that tells me that if I was to solve the differential equation, I should expect to get an equation that has cosine in it, or e to the x in it, based on the shape of this graph. Thank you guys so much for watching. I hope you have a wonderful afternoon, and I will see you for some practice tomorrow.